what these terms mean. What is the cloud? The cloud is simply a collection of commodity servers, regular servers that each have a lot of CPUs and storage and memory and disk space and so on, connected with a high-speed network. So all of these servers are hosted in dedicated warehouses called data centers, right? And these servers can expose all of this compute and storage capabilities to the rest of the users on the internet. This is the cloud. And what is virtualization? Virtualization is a technique by which you can run multiple virtual machines or VMs inside a single physical machine. That is, if you are a user of the VM, you are given the illusion that you have the full hardware, the full server machine to yourself, whereas in reality, multiple VMs are sharing the same underlying hardware. So containers is also another virtualization technology, much like virtual machines, and you can think of containers as lightweight VMs. So all of these techniques of containers and VMs together is referred to as virtualization. So what is the connection between virtualization and cloud computing? Virtualization is a building block for cloud computing. You use virtualization techniques in order to take all of these commodity servers, divide them into smaller slices, and expose them to the users of the cloud over the internet. Right? Without virtualization, the cloud would not be a very profitable idea. And with virtualization, multiple users can share the same cloud server, thereby giving us the benefits that come from cloud computing. So in addition to sharing the compute of the cloud via virtualization techniques like VMs and containers, the other important aspect to understand about cloud computing is how to manage large amounts of data. Most cloud applications store a large amount of data within these servers in the data centers. And managing this data, these techniques are called cloud storage or big data systems. This is also a big part of managing and running a cloud computing system. So this course on virtualization and cloud computing primarily has two parts based on what we just discussed. The first part of the course primarily deals with how virtualization works. That is, you have multiple servers, each of which has multiple VMs. So how do you build these VMs to run effectively on the physical servers? How are these VMs managed? All of that is dealt with in the first part of the course. And the next part of the course covers the basics of cloud storage frameworks. So how does cloud storage work? How do you efficiently store and retrieve data in the cloud? And we will do a few case studies of popular cloud storage system to understand these principles. Right? These are roughly the two parts that we're going to study in this course. So before we go into the technical details of how virtualization and the cloud works, let us just get a motivation for why do we need cloud computing to begin with, right? So all of you must have heard about public cloud providers, right? Amazon, AWS, Microsoft Azure, Google Cloud. All of these are public clouds that are available in data centers managed by these companies that people like you and I can connect over the internet and access the compute and storage facilities in these clouds, right? So all of these companies take care of providing the CPUs, memory, disk, whatever is required to set up the cloud. And this is made available to users over the internet. So these are public clouds. You can also have private clouds. An organization can just run a cloud for its users and not expose it to all the users over the internet, right? So these are two types of clouds. So the question comes up, why don't you just run an application directly on a server, directly on these servers, which are not on the cloud, are typically called bare metal servers? Why don't you just run an application on bare metal? Why do you have to run it on the servers of somebody else? Why don't you just buy a server yourself and install your application on it? So there are multiple reasons why cloud computing has become popular, right? So the first one is multiplexing gains. Multiple VMs can share the same system resources. So if you and your friend, each of you buys two different servers, then you have to spend money for these two servers. On the other hand, both of you can get VMs on the same physical server and have the illusion that you have two servers, right? So that is the multiplexing gains. And this gains comes from the fact that most of the time people are not using the machines 100% at 100% utilization, right? There is some spare capacity that can be shared, which gives you these multiplexing gains. The other reason why organizations usually migrate their applications to the cloud is this low overhead of maintenance, right? You don't have to buy the hardware, you don't have to update the software. All of this is done by if you're using a public cloud, it's done by the public cloud providers. And you as a user can simply log into those machines and expect that the hardware and software will be up to date. So the other reason is flexibility. If you have a VM on a physical machine, if the physical machine fails, you can migrate this VM to another physical machine, right? The cloud provider will take care of this. So you don't have to really worry about, oh, the disk has crashed, the CPU has failed, and all of that stuff, right? Using setting up applications inside VMs gives you this flexibility of moving to any other machine. And the other reason is also lowering of cost. You can only pay as you use. Suppose you are a startup company that only uses your web server occasionally, you have very low traffic, then you can just buy a slice of a server in the form of a VM on a cloud and not pay for the full server. You need not invest in the full server if the server is only lightly used. That said, these are all the advantages. There are also some reasons to not use the cloud. The cloud is not the model for everybody. So these disadvantages are basically performance. So if your application is running on a server next to you, you might get better performance as compared to if the application is running on a server far away that you have to access over the internet, right? So there are certain disadvantages also of running applications on the cloud. And finally, if you are using the cloud VMs heavily, then you might be paying a lot. And in such cases, you might be better off just having your own servers fully dedicated to you, right? So it is not a clear-cut case that all organizations should run all applications on the cloud, but there is a good enough case that the concept of cloud computing has taken off in a big way, especially in the last decade or so. So let's get some terminology with respect to virtualization clarified. So in this course, we will study system virtualization. That is, how do you run one full system, that is an operating system and all the user space applications, everything, over another system, right? So that is the kind of virtualization we will study. We will not study process virtualization. That is, how do you give a single process the illusion that it is running on a different architecture. For example, if you're familiar with Java programs are compiled to run on this imaginary machine called the Java virtual machine, so that the same compiled program can run on any architecture. So we are not going to study how this kind of virtualization works. We are only going to study system virtualization. And for us, the main focus is this piece of software called hypervisor or virtual machine monitor. So what is a virtual machine monitor? It is a piece of software that allows multiple VMs to run on a single physical machine. And a good chunk of this course is about how these VMMs are designed, right? So this is the model we are looking at. There's an underlying physical machine. Then there is the hypervisor. And on top of this hypervisor, you can have one or more virtual machines. So this hypervisor allows these virtual machines to share the underlying physical machine. And how this is done is what we're going to study in this course. So some more terminology. The operating system that runs inside the guest is called the guest operating system, and the operating system that runs on the physical machine is called the host operating system, right? And there are two types of hypervisors. In a type 1 hypervisor, the hypervisor directly runs on the hardware. There is no host operating system. There is only the virtual machine, one or more virtual machines that directly run on the hardware. So the type 1 hypervisor is taking on the role of the host OS as well, right? On the other hand, a type 2 hypervisor is simpler. The type 2 hypervisor runs on a host OS, which itself is running on the hardware, right? So the type 2 hypervisor does not have operating system functionality fully. It depends on an underlying host operating system for some of the functionality, right? So this is a minor difference. The principles that we study in this course will apply both to type 1 hypervisors and type 2 hypervisors. The only difference between these two is that the type 2 hypervisor leverages some of the underlying host OS functionality like scheduling, memory management, and so on, and therefore is slightly simpler. Whereas a type 1 hypervisor directly runs on hardware. So you can think of this as a virtual machine monitor plus an operating system built in together. Therefore, these type 1 hypervisors are more complicated. But as far as our focus on underlying virtual machine, as far as our focus on understanding virtualization is concerned, both type 1 and type 2, the concepts we study will apply to both type 1 and type 2 hypervisors. So what are some of the challenges in performing this virtualization? Why is this such a big deal? So an understanding of operating systems is a prerequisite for this course for this reason, right? So normally if you've taken an operating system course, you know that any operating system expects complete control over the hardware. Okay, so user applications make system calls to access the underlying hardware. User applications do not have direct control over the hardware, and the guest operating system sits between applications and hardware and mediates access to all the hardware. And it expects to have full control over the hardware. But once virtualization comes in, that is no longer the case. Multiple guests should share the same hardware. Therefore, a VMM cannot give any one guest full control over the hardware, and a guest should learn to share the hardware with other guests. But existing operating systems are not prepared for this. So if you know how existing operating systems work, they assume full control over the hardware, and therefore they are not good at sharing the hardware with other guests. So a main challenge in this course is how do you trick an operating system into believing it has control over hardware, but at the same time ensuring that it does not have full control over the hardware. Therefore, understanding how existing operating systems work is a prerequisite for this course. We will build upon this knowledge and then understand how to trick these guest OSs into sharing the hardware with other guests. Is that clear? So we will study, so there are multiple ways to do this tricking. There are multiple ways to design virtual machine monitors. And in this course, we will study several of these techniques. The most popular one today is what is called hardware assisted virtualization. This is what is used in the popular KVM hypervisor that comes with Linux operating systems. So in hardware assisted virtualization, the CPU has a special mode in which to run virtual machines, and there is support for virtualization, and VMMs are built using this support. And this is the most common model that is used today. Now, before this hardware support came up, people still built VMMs and hypervisors, most notably VMware. And the technique that was used then is what is called full virtualization. That is, this is a way in which you can run an existing operating system as a guest OS, but with the hardware providing no support at all, right? This is a much harder thing to do than hardware assisted virtualization. So even today, when your underlying hardware does not support virtualization, we have to use this full virtualization technique in order to run operating systems as guest operating systems with some amount of trickery to make them relinquish the hardware control. So finally, the third technique is what is called para-virtualization. In this, you modify the operating system code. The OS no longer assumes it is in full control of the hardware. The OS is aware that it is a guest operating system in a VM and it is not running directly on the bare metal. And therefore, there are modifications to the OS source code in order to be compatible with virtualization, right? So these are the three techniques we will study in the first half of the course. We will understand if there is hardware support, how is virtualization done? If there is no hardware support, how is virtualization done? And if the OS code can be modified, how can virtualization be done? These are the three techniques we will study in this course. And this virtualization applies to all the hardware resources, to CPU, memory, IO devices. All of this have to be virtualized. The CPU has to be shared between VMs, the memory has to be shared, the hardware devices have to be shared. And these techniques apply to all of these hardware resources. So roughly the first half of the course is going to cover all of these virtualization techniques.